In this video, we are going to get back to looking at matrices, specific examples of matrices, and more matrix concepts again. We've taken a little bit of time talking about more general vector spaces and how we can use coordinate systems to map more general vector spaces onto Rn so that we can start to apply all the information we've learned about matrices and then do whatever kind of modifications we need to do, and then take it back, use that coordinate system to get back to where we, into the arbitrary vector space. Today I want to look at one of the things that turns out to be really significant in terms of what happens when we do matrix multiplication. And for that, I want to look at an example. I'm going to look at the matrix A is equal to 3, -2, 1, 0. And let's first look at a vector u. That is, let's just look at -1, 1. And if I take A times u, well, that's going to be 3, -2, 1, 0 times -1, 1, which is going to I go across the rows of the matrix and down the columns of the vector. So I get 3 times -1 is -3, plus -2 times 1 is -2, -3 plus -2 is -5, and -1, because 1 times -1 is 0, plus 0 times 1, 1 times -1 is -1, plus 0 times 1 is 0, gives me this -5, -1. And so this is the vector AU. And you'll notice there's nothing particularly special about it. It changed that vector. It made it, in this case, it made it longer and changed what angle it's at in the plane and all of those things, but it has made this change. But if I look at another vector, V, that I'm going to look at, that is the vector 2, 1, and I take AV, something special happens. And that is AV becomes 3 -2, 1, 0 times 2, 1. And if I multiply this out, I get 3 times 2 is 6, minus 2 times 1 is -2, 6 minus 2 is 4. And 1 times 2 is 2, plus 0 is 2. Notice that in this case, AV is equal to just 2 times the vector V. All this matrix multiplication did in this case is double the length of the vector V. Now, this does not happen in general. As you saw with U, it did not happen. However, this leads to a definition. Because there are some vectors that some matrices do this kind of just multiplication piece. So the definition says that an eigenvector of an n by n matrix A is a non-zero vector x such that A times x is equal to some scalar that we will call lambda times x. So all it's done is scaled up or scaled down, depending on whether lambda is greater or smaller than 1, the vector x. If lambda happens to be 1, then it means that this matrix multiplication did nothing to that vector. So some eigenvectors, a matrix will just scale it, and we call those eigenvectors. We call those some vectors the matrix will just scale it. we call those vectors eigenvectors. The scalar lambda is called an eigenvalue of A if there is a non-trivial x, and what we mean by a non-trivial x is an x other than like 0. So a non-trivial x of, if there's a non-trivial solution, sorry about that, a non-trivial solution x of a times x is equal to lambda x. So non-trivial solution, we're saying other than something like just x is equal to the 0 vector. So if there is some lambda, some vector such that ax is equal to this lambda x, then we call lambda an eigenvalue. And if there is that vector, we say that that vector, such an x, is an eigenvector corresponding to lambda. So in general, figuring out what the eigenvectors and eigenvalues are of a matrix is a somewhat difficult task. It's not horribly difficult, and we will learn how to do that to a certain extent. But there are some valuable ideas that in some cases make this very easy. So we have a theorem that says the eigenvalues of a triangular matrix in other words, of a matrix whose entries are all 0 below the diagonal or above the diagonal. It's a triangular matrix. The eigenvalues are the entries on the diagonal. So if you've got a triangular matrix, it's easy to find the eigenvalues. The next theorem that is significant for this is that if V1, V2, etc. through VR are eigenvectors that correspond to distinct eigenvalues lambda 1, lambda 2, etc. through lambda r of an n by n matrix then the set V1, V2, etc. through VR is linearly independent. So we're going to stop here. I'm not going to work through a lot of specific examples of finding these eigenvectors and eigenvalues, but just today it's just a quick introduction to the idea. And the basic idea is sometimes matrix multiplication for a specific matrix for some specific vectors is the same thing as scalar multiplication. And when that's true, we call those vectors eigenvectors, and the scalar that you would use we call eigenvalues. And if you look at, so each eigenvalue will have many eigenvectors, but if you look at one eigenvector for each scalar, for each eigenvalue, those eigenvectors are linearly independent. That's the big idea. In our next video, we will talk about the characteristic equation, which will give us a way to figure out the eigenvalues. And once we've got the eigenvalues, you can use the equation ax is equal to lambda x, find solutions to that equation to find eigenvectors. All right, that is where we are going to stop.